Okay. Hello, my name is Alexey, and I would like to present our work about using algebraic data types in deep learning. So let's begin with algebraic data types. It's some kind of abstract description of structure of data, and it actively used in functional programming, also used in analytic combinatorics and databases. In this approach, type constructed using algebraic operators and constructors. The two popular operators, it's sum and product. So product denote product of types. So it's a composite data type from other types. For example, in machine learning, we can express iris type as a product of types of its features, like sepal length, sepal weights, and so on. Sum type, also tagged union, is a union of types. It's like union interface enum in programming languages, non-functional programming languages. So in machine learning, we can express, for example, category, in this case it's iris species, as a sum of its values. So it would be setosa plus versicolor plus virginica. In this paper, we need to introduce a new type. Okay, it's a regular type, but it didn't used in abstract data types researches. So it's a regular vector of numbers. It can be used as an intermediate state, as output, input, and so on. And epsilon or empty type can be thought as a zero-dimensional vector. Another way to describe, there are also constructors for complex types, for example, collections. In this case, there are two popular, one very popular and one less popular, is sequence and set. So sequence is ordered collection, and the set is unordered collection. There are also another types in ADT, like multi-set, power set, but in this case, there are only one set type, so it doesn't get considered. And also there can be used cycle type, image type, table, and so on. So image type and table is more closer to deep learning also than for ADT studies. There are some studies or ideas that structures or collections of elements like this can be represented as graphs, and after that we can use graph neural networks to process it. But first of all, graphs can't represent simple types like sum and product. And when we process, for example, set, we need to process a graph. But to process a graph, we need to process a set. So it's some kind of recursion, and it looks like instead of solved problem, it's just hide it somewhere else. But graphs are still very useful because it can work with recursive structures. Like in example, the parser tree of code, and to apply or to make embedding of a variable, we need to know where is this variable is used. So a variable is defined by its application. So in this case, this graph should be cyclic. It should contain a backward edge, and it would contain a cycle or recursion. So graphs is necessary. Also, types can be very useful if we extend it. For example, we can. It's much easier to understand a task or a data set, a type of data set that we work with by using this notation. For example, it can be useful in transfer learning, where we can automatically import and use some architectures. Also, it can be used for hyperparameter description, because hyperparameters also can be defined by ADT types. So the aim of this study is to adapt algebraic data types for deep learning. The key idea that to construct a function from x to y, we need to construct function from x to vector and from vector to y. So as mentioned above, the vector is some kind of a universal type, and it would be a terminal type in ADT notation. So we can decompose notation, recursively build architectures for simple types, and when we decompose it, we stop in the vector types, because vector types is a terminal type. Architecture from vector to vector is a regular architecture. We already know how to build such architectures. And from epsilon to vector architecture, that will be just a trainable constant vector, because we need to create function which doesn't depend on anything. So it will be constant. To produce a product to vector function, we need to use auxiliary functions, J, and we can use two approaches, concat approach and sum approach. So in the first case, we just concatenate result from the application of JI, and at the sum approach, we sum it. So first approach can be found in recurrent architectures, where the memory vector is concatenated with the element vector. And some approach can be found in transformers, where the vector of the next element is added to the positional coding vector. But actually, the concat approach is a special case of sum approach if we choose JI functions, like on this slide. To reverse it and make a product of types from vector, we need just to reverse approaches. So we can apply another auxiliary function and split the result into subarrays and apply another functions to get resulting types, and after that combine it into a tuple, or we just apply directly these functions to the input. It depends of its size. As sum is a more tricky operator, so to build function from sum to vec, we can just use pattern matching. So we also need to use auxiliary function, as mentioned above, for the much simple type, and we just need to match a type of input to select GI from our set of functions. And the function from vec to sum is much harder to produce because there we need to reverse a selection. So we need to use another auxiliary function along with gi. It's a C function, which some kind of select function or choose function, which is say what I we should use or we should choose to produce our sum of types. So this is sum of types. We need produce only one type from this sum to get sum of types. So for inference, we can use just argmax from output of this function, but it will not be differentiable, and C cannot be trained as usual if we use such approach. But if it's trained, inference will work fine. So to training such function, we can use several approaches. If we use our sum type as output and we know the correct answer, so we can use just supervised learning and directly trained C as for classification. If we can't do it, we can apply soft argmax instead of argmax and obtain a vector of weights or probabilities, then create several branches for all I, and after that consider each branch in the loss function with weights WE. So it's this approach is not good because it can create a lot of branches, so it will work very slow. So the third approach is a ReL approach where we can train CX to predict the value of quality function, and it be trained by reinforced learning. So at each step, for example, I can be chosen randomly with probabilities from soft argmax, and after it, only one branch would be considered. And interesting note that in this case, abs to sum function would be equivalent to multi-armed bandit problem. For the complex type, actually there are some architectures already exist. For example, deep set for a set architecture, but also the important note that a transformer block or transformers actually works with sets, not sequence. So we can use any transformer architecture for it. And also, as for vec to sequence model, we can just we can use vec to sequence model as model for produce set from vector. Also, table can be encoded with ADT, and such architecture was presented at the same conference a year ago. So let's analyze existing architectures. For example, sequence is a very popular type, and there are a lot of architectures for it. But we can use recursive definition, and it contains only sum, epsilon, and product. So we can use it to produce architecture for sequence. But in this case, the sequence will be processed from right to left. And another difference that our architecture starts with a trainable vector, not from the zero vector. From architecture which produce a sequence from vector also will differ, because in this case, instead of looking at a special end of sequence token, it would ask a question at each iteration, should we stop or should we continue? Of course, by compare result of C function. So this should be, this is not C1, C2 function, this is C function, and the first dimension, the second dimension. Also, object, as mentioned above, can be presented as product of feature types. And if we select a special auxiliary function gi, we can obtain standard matrix multiplication from it. Also, object can be presented as a set of feature types, and wait a minute, as sum of feature types. The feature itself is sum, but object is set of features. And again, if you select auxiliary functions, right, we obtain matrix multiplication. So it's actually useful because it's proof that our standard matrix multiplication or linear transformation is invariant to permutation of features in dataset. Missing values can be also represented with or encoded with ADT. For example, in this case, we can say that weak feature or feature that can contain missing values is a sum of normal feature and epsilon. And also object is a product of features as before. So in this case, if we also select GI functions, auxiliary functions, right, we obtain the approach equivalent to approach when we adding a missing value indicator. So if a feature value is presented, for example, in this case, we obtain 5.1 times A1, and if it's not presented, we obtain A2. And for missing value indicator, we have both values for a feature and for missing indicators. So if feature is missing, a value of missing indicator is equals to 1. So we multiply, for example, our value to our vector because we perform matrix multiplication, and sum it to the another multiplication. So in this case, we obtain the same values if vectors A1 in both cases are the same. Categories, as mentioned before, can be presented as sum of its values, and for example, value itself would be equal to epsilon. So in this case, if we apply our approaches, we obtain approach equivalent to a learnable embeddings or trainable embeddings. And as for categories, users and items in collaborative filtering task also can be presented as sum. And after we select a right function, we also obtain existing architecture, for example, matrix decomposition. But of course, any trainable function can be used. We conduct experiment to test approaches mentioned before. In this case, we consider missing values imputation task because these tasks require both product, sum, and epsilon. We use 459 medium-sized dataset from OpenML. This dataset initially doesn't necessarily to contain missing values, but we edit it by two ways. At first, we randomly select values which would be missing, and in the another approach, we marked values as missing if it exceeds some certain percent line. So in both cases, for each data set, we add 25 missing values, 25% missing values, 50 and 75. After that, all data sets were imputed by different imputers from sklearn scikit-learn library, and also these imputers were running with standard parameters and with addition of missing indicator. So such imputers would be named with the suffix wi. We use the same model for each experiment. So for imputed data set, there was a simple model, and for not imputed data set, there was an ADT-based model where the first layer was replaced with a layer generated by ADT notation. Another experimental setup also was the same. For all runs. So for randomly punctured datasets, approaches that adding missing indicators were worse than approaches that doesn't add missing indicators. And the ADT-based approach was slightly worse than others. But if position of missing values itself contains some hidden dependency, in this case, approaches that add missing indicator were better than imputers that doesn't add this indicator. And ADT-based model performed better than the others, especially in the data sets where a lot of missing values were added. So in conclusion, ADT can be used in deep learning because it adds safety in types, and it can take into account invariance in data. But the very big drawback that our objects will be differ by types, maybe. No, by types, by structure, and it can't be batched for gradient descent. So there would be a much poor parallelization, especially in GPU, because GPU use SIMD parallelization, where each operation should be the same for all data. For future work, we're planning to fully implement all functions. For example, vec2sum function, because it's much harder to implement it, because it need to patch or to add a new dependencies maybe in existing deep learning frameworks. And also we're planning to automatically generate models by ADT, like in NAS approaches and others. And also the out of scope of this presentation that we can take differentiation of type in algebraic notation. So maybe there also interesting results can be obtained from it. So that's all. Now I can answer your question. Thank you for your attention.
Do we have questions from the audience? Yes, please.
Thank you for your keynote. I have one question. Maybe I didn't get your idea clearly, but what is the difference between your ADT model approach and machine learning approach? I asked it because if I get you clearly, ADT is representation of machine learning algorithms. It's like a notation.
No, it's a representation of type.
Yes. So
not algorithm.
But you
actually we can present a functional type. For example, we can if we make function from A to B, we can use B with the power of A as algebraic notation from function, but it's a much complex type.
But you, yeah, for example, you annotated transformer block with your notation.
Transformer? No. You mean that transformer block is a function from set X
Yes.
to set Y? So, and what's wrong with it?
No, nothing problem, but I didn't get what kind of algorithms is it? Are it?
Transformers?
No, your ADT models.
For example, okay, there are no ADT model for set type because it's a constructor. In for example, analytical combinatoric, we can represent set of X as a sequence which can be permuted because we it doesn't consider order of elements in set. But in this approach, maybe we can do it, but in this case, set is also some kind of terminal type. So if we have set, we can use existing architecture to produce a vector from set from set, or produce a set by vector from vector. So when we find set, we stop producing new models, new architectures. And for example, like in this slide, the sequence can be represented recursively with ADT types, and we can obtain some architectures from it. But of course, it's much easier to stop producing architectures when we find sequence, because we already know how to work with sequence.
I'm seeing on the definition and notation on your slides, but I don't see any algorithms to solve a problem. Yes. And
what problem?
Your last slides contains any results? Oh, previous slides, of course. Experiments, yes.
Actually, there are two groups of results, theoretical results here. Okay, maybe this is an existing result.
I was thinking
that,
about
sequence
experiments result.
experiments.
Okay, colleagues, I think that we could stop the discussion. If you're interested, please contact Alexey and you will have productive discussion, I'm sure.